molecular replacement kind of log likelihood gain scores, R3s, emit maps, and other ways of looking at the quality of your data. Now, the stuff I'm going to talk about fits in here, right before merging. So once we've merged, we've lost the fine-grained information. Now, if I have poor CC1/2 statistics at high resolution, I don't know necessarily if that's because all my images are somewhat poor, or because they're all fantastic, but then half of them are different to the other half. They can both give equally bad statistics, but we don't have information about their level of granularity. So this method informs on what, not why, no numeric variations, which is why, hopefully, by understanding the variation in your data set, you begin to make better choices about your integration and processing parameters. So it can be a bit frustrating. So the goals for developing this toolbox, essentially, were to be able to give better real-time feedback during Excel data acquisition, to be able to identify patterns in the integration solutions, and to really just get a feel for levels of variation we have in integration results before we merging. It's about equipping you with the tools you need to be able to make better choices. So what do we have? I'm going to go through a series of small command line tools which are shipped with the CCTBX.xfel, and they act, as I said before, after the integration step, before the merging step. So in the CCTBX.xfel lingo, they act on your integration pickle files. And there are tools for looking at indexing solutions and optimal target cells, also looking for any orientation or bias of the crystals, and looking at intensity distributions of partial reflections. And in particular, I'm going to mention a little bit how this ties in with your choice of spot finding parameters in a perhaps disturbing way. So, onwards. So the first tool is cluster.unit cell, and this is essentially doing a hierarchical clustering of the per frame unit cells. Now, when you do a hierarchical clustering, what you're doing is you're taking all your unit cells from all your images, and then you're going to create a big square n squared distance matrix of them. And now, a key thing there, of course, is how do we define the distance between two unit cells, A, B, C, alpha, beta, gamma? Now, if you just take a naive approach to this, there are many potential pitfalls. For example, in some symmetry cases, you can have B and C, and if you flip them around, you have the same unit cell, but if you took the Euclidean distance, they'd be very, very different. So in order to overcome this, the first thing one can do is reduce it to the Nigli setting, which is unique. And then I also use a distance metric developed by Andrews and Bernstein, which is just implemented straight through their code. And that's a very symmetry-aware way of defining the distance between two unit cells. And we can talk offline about how it works if you're interested, but this solves that important problem. Then we interactively set the clustering threshold. You can use it with no target to find a consensus unit cell. So from here on out, I'm going to use some data from the Brunner group, which on a vesicle fusion complex. There are about 800 images, and they were collected using a goniometer setup at XPP. So this is what your unit cell clustering typically looks like. So this is the same dendrogram with a linear and with a log scale. Now, for people who aren't familiar with this, a dendrogram is a way of representing a hierarchy, how different things are. So if you take any two images, say an image from this black population and this green population, where they join represents how different they are as you go up the dendrogram. So the ones here in green, you can see, are all really quite similar to each other, but the black ones and the green ones, well, they're up here in terms of difference. And the first thing that jumps out is there are actually two populations. This is one data set, one large data set from an experiment at XPP, and we have two crystal forms. We have a long cell crystal form here and a short cell crystal form. So this does happen. If we look at the output from here, I just want to bring your attention to these two clusters, which is the short cell crystal form, that was the black one, and the long cell, the green one. Now, in this case, you can see that if you actually swap B and C and then double the new C, you get the same thing. So it's roughly a doubling, but with a different symmetry, and actually in this case, a different unit cell contents. So it does matter. What we can then do is take one of these targets, take, say, the long cell one here, take the median of the cluster and use that as a target to improve your indexing rate. And now from having 360 images indexed, we're now getting 430. And the improvement you can get can be anywhere from this kind of order, and you can sometimes see double or more images indexed when you have a good target cell. This is something, the idea of using a good target cell is something which is not new. Tom uses this an ABC alpha beta gamma histogram approach to do this, but this gives you maybe more fine-grained detail and an understanding of the relationships between multiple populations. So here we're getting a much better and also a nice level of homogeneity there. If we use the short cell, you get 97 indexed, of which almost all are in this central cluster, and you get a few like weird outliers at the side. Okay, so the next tool, orientational bias. Now, particularly with goniometer setups, you can merge your data, you can look at a reciprocal space map using something like the Phoenix tools, and you can say, yes, this wedge of reciprocal space is missing. And then you'd be like, well, how can I actually fill that wedge? And it's not immediately obvious. So the way I've developed this is such that it's in the lab frame. So if you imagine a globe which you've unrolled, and you've got the beam going down the middle here, what you do is you plot each of the real space A, B, and C axes as a dot. So for example, a dot here would be like, the A axis is pointing this way relative to the beam in the lab frame. And then you expand it for symmetry. So because by symmetry, if my A axis is pointing here, for example, I may not need to sample over here. And that's what the heat map underneath shows you. So here, actually, we can see that, for example, with the C-axis is almost always at plus and minus 90 degrees, sort of orthogonal to the beam. So there are some issues.
Where's the third axis? You've got two axes at right angles to each other in B. Where's the third axis?
See?
You've got to have three directions in a crystal.
A, B.
Anyway, psi equals 0 and phi equals 0, you've got one axis, and then you've got another axis in the middle, but not the third axis.
Okay, yeah, so one's here.
Not in that diagram, but in the the lower two diagrams.
Yes.
So how can you have a crystal with only two directions, unless it's a two-dimensional crystal?
So maybe I'm not explaining well what this is. A single crystal will have one spot here, one spot here, and one spot here, yeah? Corresponding to where the A-axis is pointing, where the B-axis is pointing, and where the C-axis is pointing. So, for example, it could be here, here, and here.
I couldn't see whether here, but they have to be 90 degrees apart, I think.
In a space group, yeah.
How can you get 90 degrees apart in the vertical direction? Not possible.
In the vertical direction? Well, I mean, you're going from you're going from minus 90 to 90 on north. It's like being on a globe, right?
Well, I think that the color code is how you get most of your decisions.
The color code is just when you symmetry expand it. Maybe we can discuss this afterwards.
Can you point with your hand instead of the pointer?
Yeah. Well, yes, but so you can have, say, this spot, and then that spot, and then that spot. So one crystal has got 3 spots, one for the A, one for the B, one for the C. Yeah. Okay.
So I think where there's blue, there's no spots.
No, not no spots. There's a lower density of spots. So maybe that's a bit unclear. So the blue is just normalized. So actually here, because here it's more dense, it goes up higher than the others. So I think it's a color bar scale thing. We'll talk about this afterwards. But either way, this informs you. So when you're actually online, this can give you a sense of, am I getting orientational bias either because crystals may be aligning in a jet, or am I getting orientational bias because of the way they're sitting in the loop if you're using goniometer, or if I'm using some kind of microfluidic device. It gives you immediate feedback about this, and also because of the geometric representation, hopefully actionable feedback. So in the sense that, if we know all our things are such that the A-axis is here, well, maybe we need to try and get the loop in a different angle and approaches like that. So the idea is to give you an actionable piece of information. And now we're going on to the intensity distributions of partial reflections. Right. So here what we want to look at is, for a single frame, what is the, pseudo-Wilson plot? So you're looking at sine theta over lambda squared against log I. And you're plotting all the partial intensities. and then a rolling average, and then a linear fit going through these. And you can just scroll through. So what does this actually tell us? So here what we have is a single frame from this test data set, which was attempted to be indexed using a spot area from 1 to 10, and a spot height from 1 to 10. And it indexed in all these 1, 2, 5, 7, 8, 9, 10, these 12 different ways. So we've got many different indexing solutions. Now, if you'd use one of these, any one of these would count as a yes, it indexed. But they're hugely, hugely varying in terms of the actual spot points. And this is actually kind of worrying, right, when you think about it. So they have such a wide, we have a very wide range of spot finding parameters that will give a successful index, but yet and there's also within that successful index subset of spot parameters, there's a very wide range of data quality. So if we actually scroll through a few of these, here we're looking at height 3, area 4, and then area 6, area 7, area 9, 10, going up to height 4, area 2, 5, 1, height 5 now, area 1, 2, 3, height 6, area 1, and height 8, area 1. So all of these indexed, yeah.
Are you looking at the found spots or the predicted spots?
So these are the predicted spots. Now, I don't entirely know what to make of this, and it's an interesting thing for discussion. But the point I really want to bring home is that there's really a wide range of variation in the integrated spots that we have, and that we have a much wider net than we may have thought previously about these. Now, you can also, using another tool, get a quick plot of all of those. So what we've done here is we've taken every single partial reflection from every single one of those 10, and we've put it here, and we've done a similar process. And you can also look at the distribution of those sort of pseudo-Wilson scale and B factors. So these all come up with this toolkit using this thing. And if we actually do that on all 800 images, you get something like this. So this is the 800 images from this data set. Every single partial intensity put through here. So it gives you a quick sense of actually, what do my data look like together. So these are about having tools that you use while you process alongside the merging feedback and alongside the earlier stage spot finder feedback that you can get to help you develop intuition for what's going on within a data set in a very quick way. And then, back one. There we go. You can also bring all of these together using the cluster.42 command, which is everything put together. So you get the top ones here, the middle ones here, and then the unit cell here. So hopefully it will be interesting to see tomorrow if people want to actually explore their data sets using these tools during the data processing workshops, and have a look at how things are, see how that helps you to guide your decisions as you go forwards. Finally, this is all implemented as an API, and the idea behind that is that, say we want to start with this big bunch of all the images that I've got that are possibly indexed. Now the question is, as Tom has mentioned earlier today, and also others, if I may have 20,000 indexed images, but the best choice may not be to use all 20,000. It might be that I want to use the 5,000 best images, and I can actually get better results that way, rather than by integrating all the bad stuff as well as the good stuff. So this, if you've got a little bit more of a technical bent, you can create very short scripts. So here within 7 lines of code, you can create a cluster from a bunch of integration pickles, select out P3, filter them using the hierarchical clustering, select out the biggest one of those hierarchical clusters, then from there pick the best subset data of that. So here what we're doing is we're saying, okay, here now we've filtered down by unit cell and we've taken the biggest hierarchical cluster. Now what we want to do is you want to say, at a resolution of 4 angstroms, given the fact that I want 90% completeness, give me the smallest numbers of images sorted by total intensity on the image that fulfill those requirements. So essentially select out the best ones that give me enough completeness at the resolution I want, and then dump those out as a list. You can then put these into either cxi.merge for merging, or into the soon-to-be officially released post-refinement program, which we're working on in the lab, which Mona's leading, just by catting that list back in. So the idea is to create this very flexible framework where you can actually interact with the filtering and clustering of XFEL data. So I'm running well ahead of time, which is a first, I think, for me. So we can have lots of questions. But to conclude, the idea really behind this is that if you have lots of experience working at a synchrotron where you have 1, 3, 10 crystals, you can use these tools as part of your CCTVX workflow in order to help transfer that intuition that is developed there onto serial crystallographic data. And these are common use cases are implemented as command line tools, and there's also this underlying API if you want to do more sophisticated things offline. Finally, this is really in like the alpha stages, so tomorrow, thank you all for participating in the first stage of alpha testing of this. This is really great to have so many volunteers. But I'm really most open to any suggestions that people have about what kind of things they would find useful from their experience. And this was really motivated. I started working on this when I was doing the data processing for a number of different people. And these are the problems that came up again and again. What unit cell should I be using? There are 2 different ones. Why am I getting some of my images indexing in one unit cell and some of them in another seemingly quite different one? Where is this heterogeneity coming from? So any other tools along those lines which people are interested in, I'd be happy to work on. Tom?
Presumably in all these graphs with the Wilson plots with suspiciously different results, the unit cells are completely different.
No, not hugely.
Because I don't know, I find it hard to believe.
Take a look.
It should be no surprise that happens if some of the indexing solutions are different or wrong.
Yeah.
But if they're all basically indexed correctly, I mean, for a start, they should have the same number of reflections. And if they're indexed consistently, they don't seem to have the same number of reflections.
Well, there's also this thresholding going on there, right?
Yeah. It's got to be something technical, so I think.
Yeah. Well, I'll show you afterwards. We'll do it all.
Yeah.
We can do some hierarchical clustering on those.
Yeah.
Right. Any other questions?
So have you used it on any SFX data, and if yes, then what's your observation?
Any SFX data? So I mean, these are. Oh, you mean like injector type data?
Yes.
Not extensively actually. Like small numbers of.
I have. And it's useful. Very big.
No.
I did it with about 10,000 images. Then you hadn't quite optimized the speed yet, so I had to set it and forget it. And then a while back, it came back up, and I was able to see my clusters. Yeah.
Yeah. So.
I mean, this is all new, so we haven't pulled this all together into a pipeline, which I think is really exciting to figure out a way to only merge the ones that are in the right size clusters.
Yeah.
So.
Well, indeed, the question of whether, if we only merge the ones in the big cluster, how much better do we get the results? When should we be? I mean, if you look at the dendrograms, there's clearly these crazy outliers. And the question is, at what point should we be throwing them out before we merge? Or if we're doing a post-refinement procedure where you are allowing the unit cells to vary, should you be keeping them in and maybe hoping that they will be brought into the fold by your post-refinement procedure? You know, so these are things which we have to experiment with and see what happens.
We have the technology. You can try varying because it's the threshold. What's the name of the threshold graph that you use?
Threshold, T.
Just threshold, okay. And so you just increase it stepwise until your biggest cluster is the entire data set.
Yeah.
Merge and solve for the R vector and just along the way.
Yeah, and also, I mean, other ways of clustering and filtering. So the idea is just to bring this all into one place, so that when you then, because every project is going to be quite different, and right now we don't know what the best way to deal with slightly heterogeneous data. And in this particular case, there really was more than one population, meaningful population. And actually, if you think about it, if you've got one cell which is half a short cell which is half the longer cell, well, if you try and integrate with the long cell parameters, some of the short cells will just be integrated as a double short cell, and now they're completely mixed in. So being aware of these things up front is a really important part of effective data processing.
People not having a number to chase. I've seen many people, they do what they can to get the indexing rate. More indexed images is better. I'm going to chase that.
Yeah.
And it can be a little bit misleading. Even pursuing CC star and R split
I agree.
Is fabulous.
I agree completely.
And it's fabulous for phase wise. So what we really need is some simple number for people to chase.
Oh, we have that. R3.
Yeah.
No, it's not.
So,
well, I mean,
So you should do 1,000 experiments and pick one that's out there, and then repeat.
Okay, a combination of, so this is a question we've been asking ourselves a lot. So the approach that we've taken as we develop post-refinement stuff for validating that is a combination of the fact that these CCs are, especially when you're doing a refinement procedure, they're kind of part of your target, right? I mean, you are refining against that. So really, the ideal thing would be cross-validation approach. R3's one, but of course there is potential phase bias. Another great one is, leave something out of your molecular replacement model, and then leave it out of your refinement model and look at the electron density coming back there. Now, I think that's probably, to my mind, that's the gold standard. So, if that's working really well, then your data really are great.
About the peak height of the anomalous difference for you.
Yeah. But I mean, the theme here is it's in the electron density, and one thing I'd really be interested to hear comment on is what is the validity of the statistical metrics we have at the merging stage presently, because they're not as robust as they are in rotation data. In rotation data, if your CC1/2 hit 50% at a given resolution, you're kind of into the nonsense. With XFEL data, I don't think, and I mean, I'll ask Nick and Tom about this, but I don't think that we can place as much faith in these things right now. So if someone has an answer, that would be awesome.
I think we can apply some faith in CC1/2 or something like that. I think they are even better than the R factor because they assume a better error model. And of course, the free electron data, they are very noisy. But so we have to lower our standards, so to say. But we can probably find a value for which CC1/2 or CC merge or something like this is significant.
I mean, CC1/2 being better than R, I'm with you, right? But I mean, when you actually look at CC1/2 experimentally, sometimes it jumps down and then it comes back up, and if you include it further out, it's especially with sparse XFEL data, it can get messy.
Nick, to me, recently described it as CC1/2 is a very good measure for precision, not necessarily good accuracy.
It's all we ever have to determine the precision. Without the external reference, all that we ever can do.
This is a statement of faith.
About noise.
So you've made a repeatable image.
Noise does not there is zero correlation. Random noise and there's not.
Is there such a thing as systematic noise?
Yeah, it's not systematic.
So the thing Anton here is alluding to is if you merge only reflections with, for example, I over sigma I greater than 0, you throw out all negative reflections. Now, if many of your measurements are if R0 is process around 0, and you cut off half of them, you'll end up with a positive number. And that positive number will correlate extremely well with itself. Don't do that. I think that's what Anton is alluding to. So if you can do this, you can see this easily in crystal. If you, when you merge, you say mid and SNR equals 0, you'll do exactly that, and you will find your CC star and your R split suddenly become absolutely fantastic, even when there's no data. And I actually added a warning on the command line to warning, don't do this. The default cutoff is 5 sigma, minus 5 sigma, because at that point there should be like half a measurement in a 200,000 diffraction pattern data set. So that really is plausible. You can maybe set it to -4 if you're really pushed, but other than that, it will really plausible.
And of course, it changes completely once you start putting in target functions and you're trying to adjust your parameters to make your intensities agree. Well, then of course, CC1/2 is going to get better. And that's
come back to the original question. You'd then be saying you made a repeatable measurement with this background. That's exactly what the R split and CC star tell you. Nothing else.
Another one is to look at how well you measure the systematic absences of roughly 0. Because a lot of fluctuation in that structure of practical data really measures what should be systematically 0 very nicely.
Yeah, but I mean, what if you have half your unit cells with systematic absence and half without, or 1% without the systematic absence? It's entirely possible.
Something else you can do is pick these spots that share the same structure factor. Like, there actually are plenty of free domains that have no anomalous values, very close to 0. You can see how consistent it goes.
I just wanted to add a comment about clustering. A few years ago, when we had these big data sets from Catepson B and Photosystem 1, we did test whether, let's say, 50,000 patterns with a very tight unit cell distribution compared to 50,000 patterns with a broader unit cell distribution, which gave better results at the end. And yes, the tighter unit cell distributions gave better results. But if you could index up to 100,000 patterns but get a broader unit cell distribution, you still won in the final quality of the data. So maybe that was the early days when Monte Carlo still meant you win because of statistics. It wasn't doubling the quality, but it did help. So we did test that out. Maybe these days with the geometry refinement and the post-refinement, this may not, maybe the difference will be more profound, or maybe adding the noisy data will no longer improve the quality. Because maybe now if we really have a tight unit cell distribution with post-refinement, with better detector geometry and detector response, maybe that really will mean a more homogeneous sampling set. So, it's just something that Carol looked at and I looked at and we got the same.
It's got to be somewhere on the continuum, right? I mean, if you have 100 great images and you throw in completely random noise, it's not going to make it better. It can't make it better. But then if you throw in slightly better, right? Where's that line?
Yeah.
Actually, you can make it better in some cases. I've done experiments with compressing images, and if you use just the right compression ratio, which is essentially adding noise, you get very basically random changes in R3. So if you pick the right random number seed, you can make your R3 a little bit better.